chill thing,
Yes,
and on the other hand has this like crazy,
I think you'll be fine if you're sitting.
and somehow they like coexist.
Right, and it's like, it's probably like the chill, comfort and chill thing is at the high level, the guys that have all the resources.
Yeah, maybe.
Yeah, it's just interesting.
It's a fascinating place. So yeah, Gordon was here last week for this.
I missed that.
But
Yeah.
he's an interesting guy. You should definitely.
Yeah, he was so interesting.
He's a he's a character. Okay, I have a good work story. So, I worked at Ames in grad school, right?
Yeah.
My first week there, he was the center director at NASA Ames
Yeah.
when I was there, and he's an awesome guy. Like I got to know him through that. And the first time I ever met him, he was dressed as a Viking with a full-up, real deal like metal helmet with the horns and a real battle axe. And I was told after seeing this that he was known to keep the battle axe in his office. If he got really pissed in a meeting, he would go like whack it into the table.
Wow.
At what point was someone like, let's have him run this place?
I don't think that's how it went. No, I think most of NASA hates him.
Yeah.
Which is
That's kind of like what he kind of said.
Yeah, I think that's absolutely true. But like, the thing was that he actually like got stuff done. And like Ames, while he was running it, was an amazing place. So I was there for like 2 years, and that was when PhoneSat happened. It's when Planet Labs spun out of Ames. Like all this stuff happened there. They were doing collaborations with Google. Just amazing, amazing stuff, and it was this really, really cool environment. They basically like one of Pete's like right-hand guys kind of like recruited me out there because they saw Kicksat online, and so that's pretty much what they did. He would like go seek out people doing crazy space stuff and recruit them to come to Ames. So it was just this really crazy playground of awesome people doing interesting things. And it was a really, really cool place to be. It is slightly less cool now that Pete's not running it anymore, but it was awesome experience. Anyway, okay, I guess I should.
Cool, yeah. Since it's not that many people, we can all introduce ourselves.
Yes, let's do it.
Do you want to start, Zach?
I'm Zach. I'm a freshly minted assistant professor of aeroastro at Stanford, and I guess I'm mostly known for this Kicksat project, which is largely what we're talking about. And, yeah, that's me.
Hi everyone, Richard Linares, aeroastro assistant professor. I started in July.
Cool. I'm Liz. I'm here at the Space Enabled group in the Media Lab. I left my job at NASA's Jet Propulsion Lab, super cool, so close to Ames. I was there for 6 years doing pre-mission formulation and also creative projects, so you might have seen like the NASA travel posters that came out a while ago. That was me. I did 2 of them.
Awesome.
And
Which ones?
So Europa and Series.
Okay.
And I brainstormed all of them. So
I have Enceladus hanging in my office.
oh no way, Enceladus was a good one.
I saw you, are you working on the Antarctica project?
Yes.
I saw that yesterday. Danielle gave a seminar at our faculty meeting.
Thanks. Yes, I do kind of both artwork and also satellite stuff. So
Cool.
it's exciting. Good to meet you guys.
My name is Eldar Shakirov. I'm a visiting student to MIT, to the aeroastro department. I'm working within a project, Work of the Future. And within aeroastro, I'm working with wholly owned systems architecture.
I'm Nick Murley. I'm a grad student in the physics department doing astronomy. And together with Manuel, we are the presidents of SETS.
I'm Manuel. I'm a second-year master's student. My research is at Draper Lab, so I work on GNC of servicing satellites in GEO.
Hey everyone, my name is Abdulaziz. I suppose the only undergrad here. I'm a sophomore in course 16. I worked in the space systems lab over the summer, working on wafer sets. You've probably heard of it. I think we met briefly in David's office. Yeah, that's all.
So my name is Anatoly. I'm a visiting student at aeroastro in Space Propulsion Lab, and I'm trying to create a thruster that's able to operate over the atmospheric gases.
My name is Will. I'm a first year master's student in aeroastro under Kerry Hoy. Primarily I work on her laser communications projects and any other projects she throws my way. Yeah, it's a lot. But yeah.
Cool. Nice to meet everybody. So yeah, feel free, since it's a small small group, just, you know, shout out whatever you want, whatever. Okay, cool. So I kind of like to start this one out, this talk out with a question, which is, what if flying a satellite costs less than a smartphone? And I think this is actually like a deep and interesting question if you think about it, because, you know, I think we're super used to everything being super expensive in aerospace, right? And people worry a lot about redundancy and reliability, and I think there's this sort of vicious cycle, chicken and egg problem there, where everything costs so much because it has to be so reliable, and on the other hand, we want things to be super reliable because they cost so much to launch, and I think if you could somehow break that cycle, I think a lot of interesting things could happen, right? So here's a few things I would do if for example, we could launch satellites for less than a smartphone. First one is ag. So probably a lot of you know that ag is actually the second largest consumer of space of imagery taken by satellites, right? After national governments. You can tell all kinds of interesting things like soil nitrogen levels, moisture, crop health, all kinds of good stuff from this kind of data. And right now this stuff is largely being done by people like Monsanto, who kind of buy this data, mine it, and they actually are now administering fertilizer and watering crops at the square meter level when they have this data. And that's the goal of these kind of people. It turns it into, you know, a data mining operation. You just take the imagery, you can optimize all this stuff, and they make more money this way because they can use less water, less fertilizer, and get higher crop yields, right? But right now, it's only the mega corporations like Monsanto who have access to this kind of stuff.
Do they own a lot of land to do it, or do they collaborate with farmers?
Yeah, no, I think there's actually these huge, in recent decades, I guess, in a lot of the Midwest now, a huge amount of the land is owned by a tiny number of these sort of mega corporations. There's no more family farms, basically, which is kind of sad, but that's what's happened. And they can afford to do this kind of stuff. But you can imagine this could be super helpful in arid climates in the developing world, things like that. And most people don't have access to this kind of stuff now because it's too expensive. Another one that is obvious is that we get tons of weather data from spacecraft, right? And there's a lot to say about this. One is that the NOAA satellites are aging and not being replaced, and that's bad. And another thing is that one of the sort of best emerging technologies for climate modeling, weather forecasting, all this stuff is GPS occultation data. Is everyone here familiar with this stuff? Is anyone not familiar with GPS occultations? Okay, so the basic idea is you catch a GPS, so this is the Earth, like the atmosphere is up here. You catch a GPS signal glancing through the atmosphere from a low Earth orbit satellite over here that has a GPS receiver. And by looking at these signals, you can tell the sort of temperature and humidity of the entire atmosphere, right, from sea level up. And this data is one of the best sources of data for climate modeling, weather forecasting, et cetera. The problem is that you have to get the geometry between the GPS satellite and the LEO satellite receiver to line up just right to get one of these measurements. And right now there aren't enough GPS receivers in orbit to do this kind of stuff. So ideally you'd have, you know, hundreds of thousands of these things blanketing the Earth to get these measurements all the time. Another one that I've gotten super into over the years and recently have kind of started playing around in a more serious way is conservation and ecology. I actually first learned how to do RF stuff from a bunch of engineers at the Cornell Lab of Ornithology, which is where this picture came from. If you squint to that board, there's a bunch of components on that that might look a little familiar if you've seen like some of my other stuff. And those guys actually do, this reminds me I should pull this down. They build some of the world's smallest radio tracking tags for animals. It turns out there's all kinds of species that migrate halfway around the world twice a year, and many of these are endangered and provide a wealth of their migratory patterns provide a wealth of information about climate change and where ice is melting and where species are shifting, where all this stuff is happening. And the holy grail in these fields would be space-based tracking. These birds, many of them migrate halfway around the world over open ocean for long periods of time where there aren't terrestrial assets that are able to track them. The existing solutions are often too big for most of the species to lift. It turns out birds can only lift about 3% of their body mass before it affects their flight. and most of these birds are less than 100 grams. So you need tags that are like gram scale for this to really work. This is a system that was developed at Cornell a few years ago by a friend of mine that was very GPS-like, but it required terrestrial base station receivers. So they put these all over Ithaca, and they could track birds wherever they went in Ithaca to like sub-meter resolution. And these weigh like a few hundred milligrams. But what happens after they fly outside of your ground base station network, right? So doing this from space is super cool. If you're into this, I have a lot more to say about this. I've got a partnership now with the WWF to try to actually do this for real from CubeSats, which would be super fun. Okay, other stuff. Disaster response is another area that I think there's a lot of potential, right? So these are interesting pictures that Planet Labs has taken in recent years. This one is from immediately after a tornado in, I forget where this was. I think this is like Missouri. This is like last year, 2017, during the tornado season. And this was basically sheer luck that the satellite flew over kind of right after this happened. You can see the track of the tornado through the fields, all that kind of stuff. This one, I think this picture ended up in the New York Times. This one made a lot of press. This was taken right after the big Kathmandu earthquake in Nepal, which was like a couple years ago, right? And Planet they were the first ones to get pictures of these things. And the reason they have these pictures and no one else does is that they have a higher revisit rate than anybody else. They have enough satellites that they get multiple pictures a day of locations on Earth, right? So the problem with most traditional Earth imaging systems, the revisit rates are really low. They only get pictures of this. They only come back around to take another picture of the same spot every couple of weeks. But you can imagine in applications like this, where there's sort of time-critical disaster response stuff, having timely data like this to be able to say, oh, that building's collapsed, we need to send a rescue crew there. Getting this kind of data in real time would be huge, right? This has huge potential impact. Some other crazier stuff that I also into, probably everyone's heard about like people getting excited about asteroid mining, this kind of thing. There's been a lot of interesting asteroid missions recently as well. They're really expensive, and part of the reason is that if you want to characterize an asteroid, if you want to understand its internal composition and this kind of stuff, you really want to go orbit it and measure its gravity field, right, and try to back out these things. And if you want to do that with a single spacecraft, you have to go capture around the asteroid. Requires lots of delta V, really complicated GNC, right, and mission ops. What if instead you had 1,000 little tiny spacecraft that you could track or just measure their relative accelerations or velocities, and you just kind of let the asteroid plow through them? You could imagine backing out the gravity field of the asteroid in one shot without having to do a delta V maneuver to capture around the asteroid, this kind of thing, right? So I think that's potentially pretty cool.
Have you heard of the, I know someone's doing like a NIAC of shooting like little chipsets into,
Yes.
I think they want to impact it as opposed to like have the asteroid fly.
So that's Justin Atchison, who was a lab mate of mine at Cornell, who was involved in some of the early stuff on this. So his idea is cool. Okay, so if you want to talk shop about it, what he's proposed is having a mothership deploy a whole bunch of daughter spacecraft in a scenario like this, and then track them from the mothership spacecraft. I think he actually proposed doing optical tracking. So if you look at the numbers on that versus deploying a whole bunch of them and having them do like sort of ad hoc mesh networking, point to point, talking to each other, basically so what you care about here and trying to back out a gravity field is the number of baselines you get, right? The number of point to point range measurements or say velocity measurements, right? Doppler measurements. And if you're doing, say you deploy 100 of these little things from the mothership, you track them all from the mothership, you're getting 100 of these baselines, right? If you deploy 100 of them and have them all talk to each other, in the limit of all of them talking to all the other ones, you get like 100 squared-ish measurements, which is dramatically better, right? So the accuracy with, if you imagine doing like a least squares fitting kind of thing, the accuracy you get from these squares goes like square root of the number of measurements. So if you have them all talk to each other, you do a whole lot better than having them talk to a mothership, right? So that's my pitch for what interesting things you might want to do. Okay, last one of the crazy ideas, and this is actually something that there's Breakthroughs is talking about this stuff if you've been following them at all. I don't know if Pete mentioned that they've been getting interested in Enceladus missions and stuff like this, right? They just signed an agreement with NASA to study Enceladus missions. So I was lucky enough to be involved in some of those discussions, and one of the things that came out of it is, it's, again, like in the asteroid case, if you wanted to go, so everyone knows Enceladus, geysers, all this good stuff, right? Maybe not, should I back up and tell that story? So Enceladus, moon of Saturn, the Cassini mission discovered geysers of liquid water spewing out into space from cracks in the ice crust of Enceladus. And Cassini, they didn't know these were there until the Cassini mission in like 2008, was it? Something like this. So they found these things circa 2008. They then planned a maneuver with Cassini where they flew through the plume and collected, sampled it and ran it through a mass spec and tried to analyze it. They didn't have kind of the right instrumentation on board to do this stuff because they didn't know it was there a priori, but they did find that it's water and it's salty, and it has interesting mineral content that's indicative of there being undersea vents at the floor of this ocean on Enceladus. And so they know all of that from what they do know. And if it's anything like the undersea vent scenarios on Earth, there's lots of critters that live in these undersea vents on Earth that do not rely on sunlight at all. So it's quite plausible that there's similar ecosystems, you know, on the floor of the ocean on Enceladus. So a lot of people who would like to go back there. NASA and ESA don't plan to go back to Enceladus until at least the 2030s. It's not in the decadal surveys. One of the reasons it's difficult and expensive, again, is if you want to go there and orbit and capture, it takes a lot of delta V, and it takes a really long time to get there because you have to do one of these complicated multi-flyby, sort of Earth, Venus, etc., to get out there, and it takes a decade if you do it that way. If instead you were willing to tolerate a single flyby, you could do it in a couple years for a lot less money and with a much smaller rocket. But then if you only got one shot to fly through, what you probably want to do is spread out a whole bunch of spacecraft and sample it at lots of points and have a variety of instrumentation, right? So yet again, a scenario in which you might imagine wanting to have hundreds of small spacecraft deployed to sample something over a large area. Okay, crazy ideas. If you have other crazy ideas, I'd love to hear them. We can chat more about crazy ideas for tiny satellites. Okay, so let's get into some of the stuff we've done. So this is a lot of the stuff I'm going to show you now is stuff that I did as a grad student at Cornell. This I actually did as an undergrad at Cornell. This is a long time ago now. This was the very first chipset that we built, and I built this actually with Justin Atchison. He was the grad student at the time, and I was working for him as an undergrad. This was the idea here was to try to make a Sputnik on a circuit board. We originally set out to make Sputnik on a chip, and that sort of got difficult. I spent a lot of time actually in trying to learn how to do nanofab stuff, and got complicated and expensive, and then kind of gave up and just did this instead. So there's solar cells on here, a little charging circuit with some capacitors, a power regulator, and a radio microcontroller chip. And this thing just chirps, and that was it. So we built this thing in 2010, 2011, and then pretty shortly thereafter got a really cool opportunity to fly a few of these on an ISS experiment called MISSY-8. This is a materials science experiment. They still do these. So this is a fun set of pictures that I always show and joke about. This picture is taken out the cupola on the ISS, out the window, of these two astronauts who are doing a spacewalk installing this thing. And if you look carefully, the astronaut on the left is holding a camera. So this is a picture of someone taking a picture of someone taking a picture of the experiment after it's been installed. And here's a close-up shot, that last shot. And these are our three little chip tap devices on there. And there's a whole fun backstory to this too. My advisor at the time, Mason Peck, got a phone call from someone at Naval Research Lab saying, hey, we have this, this PI backed out of this experiment. Do you have anything you want to fly? Oh, we need it in 48 hours. So we kind of spent a couple sleepless nights and then drove these things down and got them integrated. And it was a lot of fun. And then the other unfortunate piece of the story is that these are mounted on the antenator side of the station. So Earth is down here, and they're mounted on a nice big metal plate. And if you know anything about antennas and RF stuff, that's really bad. So we didn't get any signals from them. In fact, after I saw how these were mounted, I went back to Cornell and went and got roughed out a piece of aluminum plate, aluminum stock about the same size as this, and positioned them the same way, and tried to see if we could get anything off of them. And the answer was no. So that was a bummer. But the cool part was we got these back 3 years later. So the whole point of this experiment was to go test. You can see there's solar cells on here and all kinds of exotic semiconductor things. So the point of this experiment was to sort of expose these things to the space environment, then bring them back after a couple of years and test them in the lab. So we got these back after 3 years on orbit, and we put them under sunlight, and they turned on and started chirping right away. So that was cool. We at least got kind of an interesting data point that said the COTS electronics can survive.
Did they change color?
Yes, yeah. So we potted them in epoxy, conformal coat, right, kind of deal. And this was some space-rated clear epoxy that we got. Turned out it darkened under UV exposure. So after 3 years in space, they got a little brown. But they still worked. Thankfully, the coating over the cells was not thick enough that I'm sure it degraded the performance, but these things, basically how these worked, these cells were all ganged together in series to put out like 50 volts, and it's charging this bank of surface mount caps. So it was sized so that these guys, if they charged the bank of caps up to 50 volts, there was enough energy in there to turn on a DC-DC converter, turn the microcontroller on, and send out one chirp. So they would just charge up until they had enough energy stored to do one chirp. So probably the nasty brown stuff just made them chirp less often, which is fine. Yeah.
Was that just it's just the color? It's not like charred, right? It's just.
No, yeah, it's just that it's some chemical reaction with under UV exposure. The clear, nominally clear epoxy turns kind of brown. Which is unfortunate. Okay, so this is kind of fast forward a few years. This is the now slightly old, but these are the version that we're flying now. These are kind of old now. So I've got a few of these things. If you haven't seen them, can pass them around. They have leaded solder on them, so maybe don't lick your fingers and eat after. Pass them around. So that's what you see there.
Photos of these, or is that like?
Sorry?
Can we take photos of these?
Oh, yeah.
Or is that?
Absolutely. Yeah, there's pictures of this stuff online, whatever, it's all fine. In fact, I'll maybe talk about this later. All this stuff's open source. If you're interested, you can go on GitHub and find our board files and make your own and play around with it, and I encourage you to do that. We've had a bunch of people do that over the years. Most recently, actually, a bunch of students from Berkeley found out about this, went on GitHub, found all the stuff, and made their own boards and did a bunch of cool stuff. And we flew them on Kicksat too. So they put torque coils in them and did some other fun things. So I was pretty excited about that. Okay, so yeah, what's on these? Solar cells, and then microcontroller radio chip. This is a part from TI that's, I think, originally marketed for use in car remote entry key fob type of things. Cool. And then, yeah, there's a 3-axis gyro and 3-axis magnetometer on there. Antenna, which is made out of nitinol, which you'll see the ones that look a little different. There's sort of 2 pieces of nitinol and some epoxy stuff. The story there is that the nitinol on the antenna actually does double duty as the deployment spring to push these out. So this is what the Kicksat mission is supposed to do. The idea is to take 100 of these, pack them into a 3D CubeSat, deploy them in LEO like this, and then see what happens. So what we're trying to do on the Kicksat 2 mission, which I'll talk about a little bit more in a bit, is I guess mainly it's a tech demonstration mission. We're trying to deploy them. We're trying to do mesh networking with a bunch of them, so they see if they can talk to each other, and then also talk to the ground directly from these guys. So they don't actually relay through the mothership satellite, which people usually assume. And that whole setup with the comms and getting them to talk to the ground is a huge piece of my PhD.
Do each of them talk to the ground independently?
Yeah. So that was like a big chunk of my PhD, was figuring that out. I actually have some slides on it.
How did you do it? Oh, you don't.
Yeah, I have some slides on it, so I'll definitely talk about it. So this is a picture of the CubeSat. This is the old one. The new one is mostly the same, but down here there's a 1U bus with a bunch of avionics and stuff. 2U worth of Sprite deployer. And if you notice, there's a little hole in one of the corners on the board. And what's going on there is the antennas are coiled up and they're in these little slots. And there's a carbon fiber rod in each of these stacks that runs down here and goes through all the holes and pins them in place. And then up in here, there's kind of a top plate here, and compressed inside here, there's a big conical spring. So it's all kind of preloaded, and there's a mechanism in here with nichrome burn wires. And so we hit the button, the nichrome burn wires fire, it all gets released, the spring goes pop, and that pulls the rods out. So that's what that looks like. And yeah, the name KickSat, probably slightly obvious at this point, but this came from as a starting grad student with no money to do any of this stuff. I put this up on Kickstarter to raise the money to actually build the hardware. The launch came from a NASA program, Alana CSLI program that I think probably most of you are aware of, that opens free CubeSat launches. And here's this, just out of for fun. Here's kind of some of the things that people got for their money when they sponsored this thing. We like engraved people's names on the CubeSat structure, transmitted initials and hand call signs and things like that, and all kinds of fun things. Here's
How many tours did you have to give?
so actually no one did this one. One guy did this one, and originally
Does
this
he
was.
get a tour?
So what ended up happening for this guy, that it actually worked out great. I met him several times. He's a really nice guy. He's some kind of like eye banker in New York, but just like loves space, right? Super nice guy. And we actually ended up getting him passes to go watch the launch at KSC. And he brought his whole family. He brought his wife, kids, parents, like the whole family came to KSC.
That's worth time.
It was really cool, and he was, super excited about it. His kids loved it, and they got to meet Charlie Bolden and everything, and watch a launch. Right? So it worked out. They were, ecstatic. It actually worked out really, really well.
I bet if that was the description, you'd probably get a lot more of those.
Yeah. I did this. Kickstarter capped you at 10K for a single
person
pledge or whatever. Yeah. I think they've since lifted that. But at the time, that was, So I think he probably got his money's worth. Okay, so this is proving I actually did this stuff. This is, the side of the structure. This was, so one of the other things we did was actually send out some of these as little development kits so that people could write their own experiments and play around. And I sent out 10 or 12 of these, didn't really get much response except for a couple. My favorite one was some people from the British Interplanetary Society came up with an experiment where they would write pseudorandom data to the SRAM on the microcontroller and read it back over and over again to try to detect bit flips, which realistically in Leo they wouldn't really get any on this kind of time scale, but I thought it was clever. But otherwise, there are not too many people actually, a bunch of people sort of signed up to do it and then didn't really deliver in the end. So here I'll talk about the common story. So we want to talk to roughly 100 of these things, very low power, low gain antenna, right? It's basically an omnidirectional antenna. We can't point anything, at least not yet. And probably some of you have heard me complain at length about the FCC and RF licensing and these kind of things. So there's all kinds of issues, right? So to give you a little illustration of why this is hard, this is what the clean signal looks like. This is at IF baseband coming out of a transmitter for one of these. And so this is phase modulation. If you know RF stuff, you can basically look at this and read the bits off, right? So whenever there's a phase flip, that's a bit transition, right? This is what it looks like coming in the receiver. And to make this more cut and dry, here's in the frequency domain. This is what the clean signal looks like. If you know RF stuff, this is sort of a characteristic frequency spectrum for phase modulated digital signal. If you do RF stuff, you could look at this and say, oh, I know what that is. Here's what it looks like in the receiver. It looks like white noise, right? So this is completely buried. It's way below the thermal noise floor. It's hard. And so we play a couple tricks. Probably many of you have seen this stuff before if you're familiar with GPS, but we basically borrow a couple of tricks from CDMA cell phones and GPS. One of the big tricks is this thing called a matched filter. And this is the main piece of what's called CDMA. Who's heard of CDMA before? Probably. Cell phones do this stuff. And it stands for code division multiple access. So basically there's three ways you can sort of share airtime over a channel between many users. You can take turns talking, right? And that's called TDMA, or time division multiple access. You can put people on different frequencies, which is called FDMA, frequency division. Or there's this third option, which is CDMA, which is a little bit harder to understand and more nebulous, but the basic idea is you give every user a unique ID code, and the receiver knows all these ID codes a priori. And so imagine this is the signal coming into the receiver. In the receiver, you basically take the code you're looking for and compute a dot product, a sliding dot product. A dot product in a sliding window as the RF kind of comes through. And if the ID code you're looking for shows up in the RF as it slides through this window, you get a big spike out of this thing, right? And it turns out you can do a couple cool things with this. One is that you get an effective gain from this that's equal to the length of the code you use. So we use 511-bit codes, so you get an effective like 27 dB of gain this way. One way to think about that is when you do this dot product thing, you're essentially integrating up all the energy in this window, right? So if the window's 500 bits long, you get 500x of energy out of that, right? And so essentially what's going on is you get to integrate up the signal and the noise averages out, right? So that's kind of one way to look at it. So this gets us this kind of effective gain, and it also lets us have everybody talk at the same time on the same frequency without synchronizing clocks and taking turns or anything like that. So this is how we get everyone to talk to a single ground station all at once. And let's see. There's a long history to this that's kind of interesting. It was originally developed in the Soviet Union actually for military communication, because you can imagine you can pretty effectively obscure signals by doing this and make it really hard to find them and decode them. And then it was actually popularized by a couple of guys in the early 90s, in the very early days of cell phone technology, and they ended up going on to found Qualcomm and became billionaires. So thank Qualcomm for your cell phones and CDMA. Okay, so this is the other half of the problem. This is what the ground station looks like. So I feel like part of my sort of motivation for doing a lot of this stuff is I wanted to try doing everything as cheaply as possible and make everything available to as many people as possible. And I think not needing tens of thousands of dollars worth of ground station hardware is a big motivator here. And so all of the signal processing stuff was all designed to work on cheap commodity hardware. So this is a like $40 handheld guiding antenna and essentially like a $20 USB stick radio. Probably a lot of you guys have played with these RTL, SDR things, and a laptop. That's all you need to do this. And the receiver, so we play all these fancy signal processing tricks to do all the CDMA stuff. It's all done in software. So the whole radio is written in C++. And all you gotta do is plug in this cheap hardware to your laptop, go in your backyard, point it up at the sky, and you can actually pull these signals down from space. And we had actually a handful of amateurs that actually do this with this hardware. We put up like a how-to wiki for how to do this. And one guy was actually very successful. He posted pictures. This is someone who like worked at a tech company in Silicon Valley. He rigged the antenna up on his like gas grill in his backyard, on his like patio, and posted pictures. And he was pulling packets down, which was really, really cool. So a couple of fun shots. This was us testing this before flight out in California while I was at Ames. This is my wife who drove up a mountain with our very scientific test rig of satellite tape to cardboard and held it up to the sky. And this is what comes out of the receiver. So this is the output of that matched filter thing I was telling you about. This is at about 30 kilometers plus a whole bunch of attenuation to make it equivalent to about 1,000 kilometers line of sight distance, so to simulate kind of what you get from orbit. And so this is what comes out of that thing at 1,000 kilometers with the actual hardware. So plenty of margin, you get the nice big spike. So that's a bit coming in basically. So this was us testing outside, and then actually last summer we had a really cool flight opportunity for a couple of these on a German satellite called Max Valier. This is a research satellite built by a company called OHB in collaboration with an Italian university. So it's a kind of research satellite. But they let us hitchhike on it, and we put a couple of chipsets. There's one here, and there's one on the other side too. And they're hard mounted to the satellite, but they're independently powered and all that. So they're just put on these little 3D printed mounts. Yeah.
Yeah, I was gonna ask about those 3D printed.
Yeah.
Do you fly like that?
Yep.
Really?
This is how it flew.
Wow.
Actually, I fly 3D printed stuff all the time. Actually.
Yeah. Do you do like fully, like no, like full infill?
Yeah.
Yeah, that's interesting.
Yeah, I don't know. So I think basically I've flown stuff printed out of ABS and nylon. What is it? The Shapeways nylon and the ABS plus stuff. What's that called? Company called? But there's a couple of them are actually in the Goddard outgassing list, so they're totally fine. There's a couple of basically if you use the stuff in the outgassing list. So if you send it to Shapeways and click nylon, it's in the outgassing list and it's totally fine. Yeah. So this was cool. We flew this. This went up on a PSLV last summer, and it's in I think this is in like an 800 kilometer sun-sync orbit. So it's pretty high. It's definitely in the realm of we shouldn't deploy these up there because they'll stay up there forever.
Yeah.
So we're not doing that. That's kind of why they're hard mounted. But it was a cool ride opportunity. And this is actually the lighting. This sometimes shows up and sometimes doesn't, depending on the projector. But this was the first signals we got down from this. This is actually pulled down by some friends at TU Delft with their ground station. And if the lighting was a little better,
I tried turning them off.
yeah, it's not that big a deal. It's not that impressive anyway. It's just that this is a waterfall plot. You can see some stripes on here, which are just our signals. So these stripes are the. This was a nice ground station, not a crappy handheld antenna, so you could actually see these signals on the waterfall, but it's these sort of wideband stripes that are coming in here.
What is your data rate?
So yeah, it's low obviously, right? So it's net of all the error correction stuff. It's about 100 bits per second, but it's duty cycled. So it's like you're really, if you were trying to get like science data from these, it's much worse than that. That's when they're actually on, right? Because they're kind of like randomly waking up and turning off depending on power and all kinds of stuff. So the like net data rate over an orbit is horrendously low. But when they're turned on, it's 100 bits per second. Yeah. Yeah, that story. Okay, any questions about any of this stuff? So I was going to switch gears real quick and like get into some technically meatier stuff. So I kind of like a research theme for me that I've kind of gotten into. I do control stuff, and doing a lot of this stuff has kind of gotten me thinking about doing control, trying to do sophisticated control on very resource constrained systems, so things where you have very limited power and computation and that kind of stuff. And it's come up a bunch, so I kind of feel like this is a legitimate research theme for me. So here's one cool example. So if you saw the, maybe I should show this. So let me back up and show this video again, since there's some new phases in here. This is what we were trying to do with Kicksat when we were trying to deploy it. The original con ops, the idea was that we were going to put this thing in a barbecue roll and spin it before we did this deployment. And the idea was that we would get all of the little chipsats to come out as major axis spinners, and we point everything at the sun, spin it up, and then do this. The idea there is that if these things are spinning pancake style, they're passively stable, right? And they'll stay pointed at the sun with their solar panels facing the sun forever, thanks to conservation of angular momentum and stuff. So this was the idea, and I had to come up with a controller to actually get the CubeSat to do that, right? So we had torque coils and reaction wheels in there. And if you know anything about Attitude, that's an unstable configuration for the spacecraft, right? And you have to do all kinds of fun things. So I'm not going to talk about controller because that got involved, but this part's kind of fun. So in order to do that, we actually had to have fairly good knowledge of the mass properties of the satellite. And in particular, you really need to know where the minor axis of inertia is, where the sort of that symmetry axis is, so that you can spin it about that axis without it mutating or wobbling around. And there are very sophisticated methods for doing mass properties measurement on the ground. You can go to companies that have very specialized hardware that'll tumble the thing around and measure this stuff, but it costs a lot of money, and I didn't have access to that. So this is the sort of on-a-budget hacker way to measure inertia. It's called a bifilar pendulum. Has anyone done this before or seen it before?
Do you follow that guy, Joe Barnard? He does like thrust vectoring model rockets.
No.
He was doing the same thing with his.
Oh, really?
Yeah, his rocket.
It's kind of a classic. It's funny, I had someone at Blue Origin grill me on this in a job interview there. I was like, yeah, man, I've done this a bunch. And he thought it was some mystical thing that no one would have heard of. But it's not that most people haven't, right? You haven't seen this in a class or anything. I talked about it in my spacecraft class because it's cool and useful and cheap. So anyway, all this is you hang this thing from a pair of strings from the ceiling. That's two parallel strings, and you give it a twist and measure the oscillation period. And if you kind of linearize small angles and all that stuff, it's a simple harmonic oscillator, and you measure if you measure the frequency, you can back out the inertia about that axis. And you can do surprisingly well. Like if you do the first order error analysis and look at kind of the accuracy, it's not too bad. Anyway, but again, in theory, if you did this 6 times and sort of did some fancy estimation stuff, you could back out the full inertia matrix and get everything you needed, right? But there's some problems with this. Oh no, where did that slide go? I think I got my slides mixed up. Okay. Boo. Okay, so, unfortunate. I might have to, excuse me for a second. I need the next slide for the story. That's not gonna. Okay, I need this one. Okay, so here's what this looks like if you try to do this. So, who's seen this equation before? Some people, no one. Oh no.
Well, obviously I've seen it. But.
Yeah, none of you guys. Okay, maybe I'll skip some of this then. It's also good and kind of late. Okay, so this thing is, so who's done rigid body dynamics before? Nobody's done rigid body dynamics, like spinning tops and stuff? Oh man. Who's like...
We just taught it yesterday.
Oh yeah? Come on. Okay, so this thing is called Euler's equation, and it's the equation for a spinning rigid body, right? And so the omega is the angular velocity vector. J is the inertia matrix. This thing, the other stuff in here is actuators. So in a spacecraft, you add reaction wheels to the mix. This rho is the momentum in the reaction wheels. This is the torque in the reaction wheels. This is external torques. Okay, so this totally describes like a tumbling spacecraft with reaction wheels inside it. That's the equation of motion for that. So this is nonlinear, but if you, it's nonlinear in omega, right? So if I wanted to like integrate this, I can't do it in closed form, but it's linear in the inertia, right? So it shows up linearly here. It also only shows up once in here. So this is nonlinear in omega, right? It's like quadratic in omega, but I can kind of massage this and pull the J out, and it's linear in the J. So that's kind of what this is saying. I can like massage this equation and pull the omega stuff into a matrix and pull the components of J out into a little vector. And I can stack up this whole thing like this, which looks like a linear least squares problem, right? This looks like AX equals B. So this is, or I wrote it as an H and a Y, because sometimes estimation people do that way. So basically, this is a big matrix, this is a big vector, and if I do backslash here, right, or a pseudo-inverse or whatever, I can solve for the inertias, right? Which is cool, which is what I want. So this is seemingly a fairly nice thing, right? But there's a couple problems with this. Does anyone have any, I think this is the wrong crowd to ask this. Does anyone have any idea of what might be a bad idea about this?
H full rank.
Yep, if you have enough data, it is. There's a couple sort of subtle problems, though. Okay,
So
so
you calculate omega dot,
yes, that's one of them.
which amplifies the noise.
Yeah, so that's really bad. So you have a gyro to measure this. We don't have direct measurements of this. So if I want to do that, I have to finite difference these or whatever, which amplifies noise, which turns out to be a bad thing. There's one other, maybe more subtle thing, and it's that if I do this in a naive way, I'm just solving for this thing as a vector, and there's nothing to say that this thing has to make up a valid inertia matrix. So inertia matrices, do we know what those have to look like? Anybody?
Symmetric.
So, yeah. What else? Yes. Good stuff. Okay. Symmetric, positive, definite matrix. So an inertia matrix could be a real inertia matrix, has to be symmetric and positive, definite. All that really says is that you can't have negative mass and negative energy. It's like the matrix version of a positive number, right? It's basically saying I'm not allowed to have negative mass and stuff like that. Okay, so there's a whole bunch of math next, which maybe, given the audience, is not super useful to all of you guys. So basically, we play some fancy math tricks to get rid of the omega dot, which involves like Has people seen like Lagrangians before and stuff? So maybe this will make sense to some people. So this is called the least action principle. We've seen this before. Some of you guys. Okay. So normally you like do some fancy calculus of variation stuff, right? And you get out rate of motion. So instead of doing that, we discretize this thing first, and then you get this like discrete time version of Poiseuille's equation, and there's no more derivative in it. So you got rid of the omega dot. So that's cool. So that lets us not have to do this finite diffing noise amplification stuff. So that's what this says. These are basically like quaternion looking things. These are rotations instead of omegas and omega dots now. And then there's some fancier stuff about the positive definiteness thing, which essentially comes down to we can put a bunch of constraints on this that says that that J thing has to be a symmetric positive mass matrix. And we can solve a constrained least squares problem now, where we just explicitly enforce these constraints on the matrix and set it all up like this. So this is the original least squares thing, right? I'm minimizing. And then this is all the constraints that says the matrix has to be positive, definite, all that good stuff. So if we do all this, this is a simulation of this. This is the money plot. It's just showing, this is our method, the red that I came up with, and the blue is kind of the existing state of the art before this. And these are the errors in all the inertia components, given the same input data, right? So basically, we have lower error and do better for the same, that's the message. Okay, fancy math, do better. End of story. Okay, so that was a little rough. Maybe I'll, so no more math, I promise.
I said I like the math.
I know, yeah.
One person.
Okay. Well, we can talk about this later.
Sure, sure.
I like the method, just don't understand it. But
Okay. Well, if you want to talk more about it, I'm happy to. I won't subject you to any more of that. This is a little more friendly and fun. Okay, so this is getting to the attitude control thing. So I, like doing attitude control and GNC stuff. So when I, look at this stuff, I'm like, well, I want to point these things. I want to be able to put higher gain antennas on them. I want to be able to point cameras and sensors and all this kind of fun stuff. How do I do attitude control on these things, right? And this is, I put this plot together a while back. It was actually someone I knew from Cornell actually suggested this, making this and
Was
looking
it
at it.
Brett Schriedman?
Yeah, do you know Brett?
I read his paper on this stuff. Yeah, he works at Draper, so.
He doesn't anymore.
He doesn't?
No. Oh, Brett does. Brett does. Still
yeah.
work there. Yeah. Joe
I
Shore.
probably saw him today.
Oh, okay, yeah, sorry. No, I was thinking of Joe Shore, who is another guy from that Cornell group. Anyway, okay, so what this is showing is kind of the fraction of the spacecraft mass taken up by the attitude control system versus kind of the total mass of the spacecraft. So for really big spacecraft like the ISS, the attitude control system is tiny, tiny fraction. For ISS, it's like 0.2%. If you go towards smaller, slightly smaller sats, so like a big geocomsat, it's maybe 1 or 2%. And we go to like LEO small sats, is something in the like 100 kilogram class or something. Now it's like 5 to 10%. And when we get down to CubeSats, it's now like 30+% of the spacecraft mass is taken up by reaction wheels on a 3U. So that's not good. And you can imagine for a 1U CubeSat, it's even worse, right? You're starting to get up to like, basically there's no room left for a payload if you want to do pointing with reaction wheels on a 1U CubeSat. So what do we do about this? Anyone have any ideas?
Well, I guess the first question is why?
Yeah, so I've actually like thought about this a bunch. The like hand-wavy story is it has to do with scaling laws for the physics, so like the way friction scales versus inertia and things like this. So like inertia is like length to the fifth, right, like ml squared, and there's some friction terms that scale like surface area, right? So as you get small, friction starts to dominate, and basically making small spinning parts is kind of tough and bad generally. So you end up with like, it gets really hard to spin them faster, and we get a lot of energy dissipation or inefficient and stuff like this. But yeah, I don't have that story super ironed out.
Does it also have to do with the motors too?
Yeah, absolutely. Yeah. So I mean, but it's all tied up. I think fundamentally in these.
Basically, you can spin them at like lower angular velocities, which mean that you need more mass percentage.
Yeah, I think there's the argument is something like, I haven't had this in 100%.
It's interesting.
Yeah, I agree. So empirically this happens. And like my hand-wavy explanation is it's sort of related to like the scaling of friction versus inertia and stuff like that for these small things. But I don't have the ironclad, like I can't write you down the stuff and prove it. I need to dig into that a little bit more.
It's a good trend, yeah.
But, okay, anyway, so here's like the fun, so I hung out down the road here at that other school in Cambridge for a while with a bunch of people who were into biomechanics for a couple years. And one of the guys who met one of the guys who worked on this. So it turns out geckos, which are about the same size as these chipsats, they weigh about the same, they're really good at attitude control. And they can kind of do full 3-degree of freedom pointing by whipping their tails around. So this is kind of interesting. And it's in the right ballpark size-wise, right? And it turns out humans can do this too. There's this was done in the 70s on Skylab, which was the US space station back then. And the theoretical work was actually done by a guy named Thomas Kane, who maybe some of you have heard of Kane's equations. He was a professor at Stanford for a while. And they were funded by NASA to look at how astronauts might be able to reorient themselves if they were kind of stuck in a spacesuit or something like that. It turns out if you wiggle your arms and leg around in weird ways, you can control your pitch, roll, and yaw and do full 3-DOF attitude control. So this is a fun idea that we're now starting to work on in my lab. And this is a simulation of what this might look like at the 1U CubeSat scale. So you might imagine having little deployable tails, if you like, that can wiggle around. And you can see that this thing is wiggling, but it's also rotating about this axis. And in a second, what's going to happen is I'm going to flip the polarity on the wiggling, and it's going to rotate back the other way. So if you have 2 tails like this, you can reproduce a reaction wheel. And it turns out if you have 3 tails, you can do full 3-DOF pointing. And there's a few ways to think about this and why this, so now it's spinning the other way, why this might be a good idea. So on the 1U CubeSat scale, you can imagine if you did reaction wheels, you're bearing these little tiny wheels inside the bus. You're taking up internal volume, taking up mass, and the moment of inertia of that wheel is not very large if you packed it inside the bus. What we're doing here, Ed, is imagine taking the same amount of mass but putting it on the tip of one of these beams, tails, whatever, and sticking out like this. Well, inertia goes like ml squared. So now you've dramatically increased the inertia of your actuator. So for the same, say, speed, input power, etc., you're getting way more angular momentum out of this thing, right? So, and you freed up all the internal volume. So I think this idea was motivated very much by stuff at the size scale, but I think it actually makes a lot of sense for CubeSat size scale as well. So, yeah.
Do these tails wiggle in the same plane?
So what's going on here, I have another set of slides where I talk about this and do all the math out, which is fun, but I told you no more math, so if you want to see the math, we can do it later. Basically, so one of these is kind of, imagine wiggling in the body, say, Y direction, and the other is going in the body X direction. And so one way to think about this is, imagine I have these 2 things doing this and this, and they have tip masses, right? And now imagine I put this one cos of t, and this one sine of t. Think about what the tip mass, the sort of center of mass is doing. Both tip masses, if I do that, it's moving around in a circle, right? So you basically reproduced a wheel, right? The angular momentum, the net angular momentum of that system is doing this now. And now, what if I flip the phase between them? So now I can make the net angular momentum go the other way. I can also make it 0 if I want to, right? Just by playing with the relative phases. So I can keep them wiggling around at a constant rate and just play with, yeah. So you can do some fun things that way.
So that's just the frequency of the wiggle?
So the frequency determines what the slew rate is.
Yeah.
But the relative phase is what determines kind of the direction, and you can modulate. So ultimately, the maximum slew rate is determined by the wiggle frequency, I guess. But you can do anything in between plus or minus that max by playing with the relative phase, which is kind of cool. Yeah. All right. So how are we doing? Oh, we're like 7. So I'll kind of just zip through this. So we flew this thing. You've seen P-Pause before. We don't have to do that. The first flight of this thing was in 2014 on the 3rd SpaceX launch. Just KickSat 1 launched. It didn't quite work. It was very sad. The story is, it's a long story. I'll try to tell the short version. So originally we were supposed to deploy the ChipSat sprites on a timer, a couple days after launch. But we weren't allowed to at the last minute because the launch got delayed, and then there was a Soyuz launch right around the same time. So they told us we had to wait 16 days. I had to go take the thing out of the pod and take it apart again and reprogram it to do 16 days. Unfortunately, the mission lifetime was supposed to re-enter after 20-ish days. So 16 days was kind of a little close. And on orbit, it worked great after it deployed, but on day 14 of the mission, the bus reset. It was a single event upset kind of thing. And that reset the timer and reset everything, and unfortunately, it re-entered a couple days after that. So that was the sad saga of KickSat 1. But some very cool things did happen as a result of this that I'm still like super proud of actually. So this whole thing was kind of very open source, hackery, right? We want to get people excited about it, involved in space in new ways. One of the ways we did that was do all the mission ops out of a Google group. So we had a bunch of hams all over the world set up these amateur ground stations. Many of them set them up from our GitHub instructions with $50 worth of parts. A lot of these guys were already hams who have expensive rigs, but everybody, we put up a JavaScript implementation of our packet parser on a website, and people would just go online and upload their packets that they had gotten. And we collected everything in Google Docs spreadsheets, and we had people in this Google group doing all kinds of data analysis. So we had people making plots of the spacecraft telemetry data, like battery and temperature stuff over time. We have one guy on here who made his own orbit simulator with like sophisticated drag model and was trying to predict the re-entry of the satellite. And he actually ended up doing better than NORAD, which I guess if you know how NORAD does it, it's not that impressive. But so we got a lot of people, and this was just totally amateur, people doing this for fun in their spare time. So that I thought was especially cool that we kind of got people involved on this level. So I would like wake up in the morning and go to the coffee shop with my laptop and like look at the data that had come down from all these people all over the world every day, which was really cool. So this stuff's not that interesting anymore. KickSat 2 we just finished this thing up, and I'll show you the fun video. This is my new lab. We hauled out all the furniture and did some testing. This is what the deployment of this thing looks like in real life. And I have to say, little disclaimer, on the flight unit, there's a tether keeping that thing attached to the bus. I have to mention that that was required, which is interesting. The orbital debris people made us put a tether on there.
I know, you're throwing all this
exactly.
stuff.
Right? But they got really, so okay, that's that. This thing flew on.
What was the area to mass ratio that it like, or?
It's basically, this is in the CubeSat spec. We're not allowed to do this. And we're like, but we're doing all this other stuff. They didn't seem to care much. It doesn't have to be rational. I don't know. There's so much of the stuff that is like people in these
Bureaucrats?
Like, yeah, it's bureaucrats who are like just it's covering their asses.
This is what this form says.
Exactly. It's a lot of that, right? And they don't want to put their jobs on the line in a lot of these situations. So this went up on the Saturday before Thanksgiving. It was like a couple weeks ago on the NG-10 launch. This is an Antares rocket. I was standing 2 miles from this when it happened, which is the first launch I've done at sea, and it was really cool. Who has gotten to see a launch here? Yeah, it's really cool. You should do it. So the really cool thing about this, so I've never been on one of these. The thing you don't get from the video, it pretty much looks like this, right? But the thing you don't get is the sound. So you like feel this in your gut, and it's like this deep rumble. It doesn't sound anything like it sounds when you see it in a video. And then the other really cool thing is that we had a nice clear night to watch this, and we actually saw the rocket the entire way up to orbit. So we could see the first stage until main engine cutoff, and the light goes out. And then 30 seconds later, they do staging, you hear them talk about it over the intercom, and then 30 seconds later, they light the second stage. You see the light come back on in the sky, and then you see it go out, towards the horizon, and then you see it go out after the second stage burns out. So you actually see the whole thing, the entire, sort of power flight of a rocket with the naked eye, which is really cool. I've never, and I think that's actually not, I think it's just we have really good viewing conditions. But that was super cool. Okay, other stuff. This is our GitHub page. It now says Stanford instead of Ithaca, but otherwise looks the same. And if any of you guys are interested in any of this stuff, it's all up here. So we've got CAD models of everything, code for everything, circuit board layouts for everything. Anything to do with the projects is up here. So maybe some of it's useful. Maybe you're just kind of curious and want to check it out. I encourage you to do that. And if you do anything cool with it, let me know. And I think that's kind of all. I think we're kind of over time, so I'll just put it out there and say thanks to lots of people over the years who've helped out with this, and that's it.
So this is like, so this is all on GitHub. Have you seen, is this available all over the world, or is this like a specifically like a United States thing?
I've had people in Japan and Argentina and then various other countries make these things and play around with them and email me about it and stuff.
Awesome.
Yeah.
Can we go through the math for the like motive inertia stuff, arms thing, wiggling?
The wiggling thing?
Yeah.
Yeah. Okay. Should we like let everyone else speak their piece first? Does anyone else have any things they want to talk about? Yeah.
So I heard about this rocket that shot up, I think maybe a year ago, and then they were like all unregistered chipsets.
Oh yeah. I know those guys.
Like a quarter.
You know those guys?
That was like a quarter.
They were quarter U CubeSats. So they were 10 by 10 by like 2.5 centimeters. They're called Swarm Technologies.
Do you know if they got in like big trouble, or is it?
They got in trouble, sort of. They got a slap on the wrist, and it made all the news. And the FCC just gave them a license again for doing one use. So the big deal at the time was, oh, is this going to destroy the world? We can't track them, blah, 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 which is the FCC's been claiming about a lot of this stuff all along. So right now the FCC has an internal policy, it's Carl's policy, that they will not license anything smaller than 1 U. And there's nothing written down anywhere, there's no technical reason, there's no sort of rationale for this. It's just this one guy decided that was the way it was going to be. And so they will not license anything smaller than 1 U. So these Swarm, the story there is they're a startup, they've got VC funding, they actually have customers at DoD who want to pay them to do stuff, and they built these things, they got a launch, the whole deal, and then the FCC basically arbitrarily pulled their license because of this secret, nothing smaller than a 1 U gets a license thing that some guy in some office decided that isn't written anywhere and has no sort of basis in law, right?
Well, space fence can track that size.
They can track it. Leo Labs can track it. No, there's no problem. So they tried kind of reasoning with these guys, and basically, I think so. There's kind of fault on both sides, and they probably shouldn't have done this, but I understand where they're coming from because I've dealt with similar frustrations. But basically, they were flying on a PSLV in India. The Indians didn't care that the FCC, didn't like them and whatever, so they launched it, and they kind of were under the radar, didn't tell anybody. But it was being tracked by radar units. So the funny thing, if you go read the initial article that drove this story, yeah. So the funny part was that this was broken in IEEE Spectrum and got picked up by a bunch of news outlets. Right, it was a big thing for a few weeks. They called them space pirates and all this stuff. So the funny, if you read the original article, it says, so no one told anyone. Like these guys didn't go out and tell people that they had done this, right? And it says in you go through the whole rationale at the top half of the article is them talking to the FCC guys, like, oh, this is terrible, can't track, blah, blah, blah. And you go to the second half of the article, it's like, oh, and we know they're doing it because we've been tracking them since launch. So yeah, they're definitely trackable by radar. Like, there's not a real technical issue here. There's like a lot of bureaucratic issues with this kind of stuff. Our stuff, these things, it turns out, I have Leo Labs, which is a startup that does radar tracking. Their radar is at 450 megahertz. The comms for these things is at 437. So the antenna we have on there is actually like an excellent scatterer in the band that their radar is in. So these will show up no problem basically on the Leo Labs radar. So most of the stuff can be tracked, and it's not a real technical issue. And most of the people involved in the smaller than CubeSat world. And the other thing to say about this is people in other countries are doing this stuff routinely at this point. There's a bunch of people in Europe doing pocket cubes, which are 5 by 5 by 5, sort of shrunken down CubeSat things. So a bunch of those have launched, but they're not allowed to be flown out of the US. You can't get an FCC license to fly them in the US, but there are tons of people doing it in Europe. And China has flown stuff like this. Like there's people doing it, and I think the frustrating thing in trying to work in the US is that we have kind of hamstrung here
So to get around, you just launched in another country?
Yeah, so I showed you that thing when we flew on that German satellite. So I was always kind of paranoid about ITAR and stuff like this. But after dealing with the FCC for like 3 years and getting nowhere, it took 2 weeks to get an export license to go do that. And I put them in, I got the letter and took it in my carry-on, and that was it. So now that I know that, I'm definitely kind of looking for European collaborators.
What part of that is ITAR control?
It's simply the fact that it's space flight hardware. As soon as you call it flight hardware, it's automatically ITAR restricted. If you call it, you know, engineering hardware or test hardware or whatever, it's not. As soon as you call it flight hardware, like as soon as it's going to go on a rocket, it's ITAR. So, right. So I've taken these in, you know, my pocket all over the place in my bag, and as long as I'm just tooling around with them and whatever, and that's fine. If I were taking them to go put them on a launch vehicle, then I need an export license.
How did you become aware of that? Like,
I was like, you know, sort of working on this kind of stuff, I guess, for a few years in like a university environment, became kind of aware of the issues and stuff, and then trying to do it, you're just like, so I mean, there's enough regulatory oversight of this stuff that you have to get a frequency license from someone, right? And then they ask questions about, you know, so there's, I don't know, I guess it's just trying to do this stuff and then getting sort of frustrated by it. You learn how the game works a little bit.
So I have a question about the inertia estimation stuff that you spoke about. Did you get a problem, do you have a problem because of noisy torques when you use?
No, it's not noisy torque, it's noisy gyro measurements.
Oh, okay.
So we have a very cheap, you know, like smartphone style chip gyro, and they are very noisy and have bias and all this other stuff. So if you try to take the data coming out of one of those and just finite difference it to get angular accelerations, it ends up amplifying that noise a whole bunch, right? You know, that story. So it's really noisy and gives you really bad estimates.
Okay.
It then ends up biasing your inertia estimates in practice if you have noisier data like that. So you don't want to do that. And there's a lot of the literature in doing this kind of on-orbit inertia estimation, or in general with gyro data. A lot of it has to do with how you pre-filter the gyro data to avoid issues with noise amplification. And also, I should say, when people do this on big spacecraft, they're doing it with like ring laser gyros that are, you know, $20,000 and give you like really pristine gyro data. We're doing it with $5 gyros that are not so nice. So it's a different situation.
Okay, and then when you put constraints on the inertia matrix elements, can you do linear least squares with constraints, or did you have to do? Did you have to use a solver to constrain?
Yeah, so, okay, we can talk a little bit more about that if you want. So this problem, if you take this away, this is the linear least squares problem, right? This is, you know, residual squared, blah, blah, blah. So I have the same objective, but I've now written down all these constraints on the elements of the inertia matrix. Yeah. So this is actually, the reason this is nice, which I didn't mention or get into, is that this is a particular kind of optimization problem. It's called a semi-definite program. Has anyone heard of this? So the reason it's nice is it's convex. Yeah. Oh, okay. So that means that if you set it up right, you get a guaranteed solution, that it always converges, and you can write nice fast solvers for this kind of stuff. So you can actually do this online and count on it working, and not be scared, I guess is the message, because it's a convex optimization problem. Okay. Wiggly tail math. Is that what you want? Yeah? All right. Ask and you shall receive.
Also, so are the rods flexible in any way? Not just the tips, but...
This is just their model here is rigid links with torque at like the shoulder where they're attached. So this was a quick little talk on this stuff that I did a while ago where I had some math. So a bunch of this stuff that you already saw. Okay, so this is what's in that video I showed you, right? One of them is kind of body X, someone's body Y, let's say. Here's the math. Okay, so first off, everyone knows what a rotation matrix is, right? Isn't that? Okay, so but you guys have not seen the Euler's equation stuff for body dynamics so much. Okay, so what this is, okay, so this is a rotation matrix, R, and I want to write down the kinematics of this thing. Right? So if I wanted to write down an ODE, if I wanted to simulate this thing tumbling around, right, and just sit in MATLAB, say, with ODE 45 and write down a differential equation for the rotation matrix, right? So I could integrate the equations and simulate this thing. This is kind of what that looks like. So this is the, okay, so, probably, didn't work. Magic. It's calling me without the Wi-Fi turned on. How does that work?
You should pick up.
Yeah, I will. That's my wife.
I meant without the Wi-Fi.
Okay, so where does that go? Okay. Okay, so rotation matrix. So if I want to write down an ODE for the rotation matrix, right? Like R of t, right? If I have this thing tumbling around, this is how that looks. So R dot equals, so this is R where you are right now. This omega hat thing, oh, this is omega, the angular velocity. And this hat thing is a skew-symmetric matrix. This is getting probably a little too math heavy. If you guys start getting like, how many people are with me right now? Okay. Cool.
I don't know what that is, but I think I can follow.
So what this is, it's actually the matrix version of a cross product. And it's actually not hard to derive this thing. So it's like if you're, you've seen like in a rotating coordinate frame, if you like try to get the velocity of something in a rotating coordinate frame, you get like an R cross the offset from the spin axis, right? So there's like cross products, like omega cross R gives you like velocity in a rotating frame kind of thing. That's where this is coming from. So this omega hat thing is just omega cross. It's the omega cross product thing. And what's going on here really is that the rotation matrix, the columns of it are the basis vectors of your coordinate frame, right? So this is what this is really doing is saying all of those coordinate axes are changing in time by like omega cross. So it's just all this is really doing is like omega cross with each of the three coordinate frame vectors, right? Does that make sense? So that's the time derivative of your rotation matrix. It's really just stacked up your coordinate frame basis vectors, right? So this is essentially just telling you how your coordinate frame is changing in time, and it's really just saying it's omega cross all of them stacked up in a matrix, right? That makes sense? That's pretty much what that says. Okay, so the next step is, because if you believe me there, who's taken linear systems? You've seen like, you know, A, B matrices and
elementary version.
Matrix exponentials and stuff like that. Okay, so now what if I call this phi, or state transition matrix, and this thing A? Now what do I have? I have a linear, I have an LTI system, right? And I can solve this thing with a matrix exponential, right? So what this says is if I'm looking for R of t, as long as my omega is constant, if I'm rotating at constant speed, the solution to this differential equation is R naught, like wherever I start, e to the omega hat t. So this is just e to the at from your linear systems class, right? And this is, think of this guy as like the state transition matrix, right? And then this guy is your solution to your linear ODE, it's just e to the at. Cool. All right, so, oh yeah, and I actually wrote down the definition of this omega hat thing. Cool. So I was trying to say that in words, I didn't realize I had it here. So it's this cross, so it's sometimes called a cross product matrix. It's the thing that, if I do omega hat x, and this is what omega hat looks like, it's equal to omega cross x. It's just this cross product thing. And the explanation is kind of what I just said about, it's omega cross with all the coordinate axes.
Is
Yeah.
X a scalar or a vector?
What is what?
Is X a scalar or a vector?
X is a vector. Just all three. So R is a matrix, everything, T is a scalar. Omega is a vector. Omega has this matrix thing. And X would be a 3 vector here, right? Okay, so hopefully
That's like your basis coordinate frame?
Yeah, so R is a rotation matrix, but if you look inside a rotation matrix, what it is the
coordinate frame.
body, it's just the, like the columns of it are the basis vectors of the coordinate frame, right? So what this is saying is just that that's how those basis vectors are going to move around if the whole thing is spinning. And just don't make a cross with all of them, right? That's all that's going on here. It's just all stacked up. Okay, so next step is, so this thing, I can Taylor expand it, right? So this is just a Taylor expansion for an exponential. Blah, blah, blah. We've all seen this before. Cool. Okay, so, and what did I say here? So, right, so this is this r hat theta thing. So this is, instead of omega, what I'm saying is r is the axis. This is now a finite rotation. So I'm replacing like omega t. So you can imagine omega times a t is like a axis angle vector. It's like it's a theta times a unit vector axis of rotation, right? So that's kind of what this is. This is the unit vector axis of rotation times the angle of rotation, scalar, which is the same as an omega t. It's just writing it a different way, and I'm Taylor expanding it into theta. So this is for like small angles. This will give me, a pretty good approximation of the rotation matrix, right? For a small theta, I can plug into this Taylor expansion. Cool. Okay, so okay, so the reason to do all this is when I do this wiggling thing, this is kind of what I'm doing. What we said in the picture before is I have one in the x direction and one in the y direction. So if I do a wiggle in the x direction, I'm getting a little tiny x rotation, right? And if I do a wiggle in the y direction, I'm getting a little y rotation. And then if I undo them in the opposite order, I get the opposite x rotation, right? This is r inverse equals r transpose, right? And then the same deal on the y, right? So I can like do these little wiggle rotations and then unwiggle in the opposite order. And because rotations don't commute, right? Everyone knows this, right? So if I do like roll then pitch, if I do the same thing, pitch then roll, I get a totally different attitude, right? So if I flip the order around, I get something different. So the cool thing here is if I undo these in the opposite order, I get a net rotation out of this that's non-zero, but I've put the actuators back where they started relative to the body, right? So if I do this, then this, then this, then this, I'm back where I started in terms of the actuators, so I can keep doing that forever. And then every time I do it, I'm getting a net rotation out, right? So what's going on here is now I can like plug in that Taylor expansion for each of these rotation matrices, right? So we did that little Taylor expansion. If I do that, I get all these little Taylor expansions, right? And if I kind of collect terms and simplify everything down, this is what comes out. So what this says is after I've gone through a full sort of cycle of wiggle, wiggle, unwiggle, unwiggle, this is what I end up with at the end of the day. So what it says is, so the identity is no rotation, but I get this term that is second order. So there's this like second order Taylor expansion term that shows up. So what's the picture is, remember when I showed you the video, I was doing this, but it was rotating, there was a net rotation about that other axis. So the wiggle that was going on the other two axes, that's the linear first order term in this Taylor expansion. The first order linear term in all these guys cancels out over one rotation period, but there's a second order term that sticks around. And this is the net rotation. So what's going on here, and it goes with the cross product. So if I wiggle and unwiggle in the right way in x and y, I get a net rotation about x cross y, or z. Okay? So there's a name for this, and usually when I showed this to like kind of more control-y robotics people in the past, and so it turns out that there's all like fancy math behind this that you can give all these things fancy names. Rotations are called, or have a mathematical structure called a Lie group. Have you ever heard of this before? And the cross product matrix thing that I showed you, this thing, this is called the Lie algebra for rotations. And this Taylor expansion-y thing that pops out with a cross product here, this is called a Lie bracket, if you're a fancy math person. But it's actually not that bad. It's just Taylor expanding some stuff, simplifying. So most of the point of the story was to like tell people what a Lie bracket was and not be too afraid of it. And then if you put this all together, you see the kind of end result is this sort of wobbling motion, which is the wobble is the first order terms in all the Taylor expansions, but this net rotation that's happening in this axis, which is x cross y, is that second order term in the Taylor expansion that sticks around after a full cycle, right? The first order terms all cancel over a cycle, and the second order terms stick around, and that's the math part. The cool part about this is with all that like math that we did, you can actually predict what this thing's going to do now. So if I say, here's the wiggles I'm doing, you're going to plug into all that, and it's actually this simple equation down here. It tells you exactly what's going to happen. Right, so if I wiggle in the x direction, wiggle in the y direction, about this angle, put it all together, I can say what the net motion will be. Right? Okay. Did that make sense to anybody?
Very slightly.
For not being a controls person. That
Yeah,
kind of
I mean, this isn't standard control-y stuff either. This is like, it's a little arcane, it's a little farther afield. Okay, cool.
So how does your wiggle grow with the length of the arm?
It goes with length squared, right? Yeah. So if you keep the inertia of the body constant, it depends on what you hold constant, right, I guess.
So is this formulation assuming that the inertia of the arms are similar to the inertia of the bodies?
No, this is assuming you're like,
This inertia doesn't come into play.
yeah, so this is assuming that, this is kind of abstracted one layer higher, saying like, if those inertias are such that I can command something and get this small rotation out of one sort of wiggle, right? So this is a layer after that. So if I measure the inertias and say I've applied this torque or whatever for this amount of time, I get this much net displacement.
Yeah.
That's this guy. So it's buried inside there with the inertia stuff.
That makes sense.
I got sort of fascinated by this stuff a while back. And
That's pretty interesting.
it's kind of fun and interesting. I heard people talk about this stuff, like math people, and it's like super arcane and makes no sense. But then if you just work it out, it's actually very straightforward. Should be able to do with like a basic, like sort of first year grad student kind of math education. All right. Anyone else want to talk about anything else?
So, are you going to try and put these kind of, I don't know what you call them, the arm actuators on your chipsets?
Yeah, eventually. Yeah, so this is one of the things we're playing around with. I want to do next on these things. Yeah, I kind of like calling them tails. I like the gecko. I want to call it gecko sat.
It'd be cool to put this on that diagram. Just
Oh, yeah.
To cut the triangle.
Yes, yeah, absolutely. Yeah, so I think this is a cool thing for like CubeSat scale things as well. And I think there's in addition to the like argument that you can free up all the internal volume and probably do better from a mass standpoint. I mean, there's obvious downsides to this. You're wiggling around. You've got this like kind of residual wiggling motion that probably don't like if you're trying to do certain things. But I think
You can do this with just a hinge, right?
Yeah.
You can just put a hinge and not cut the wiggles.
yeah, you can do a bunch of things.
A hinge on the chip. And just rotate it.
Yes, yeah. I actually have another demo that's like a flat thing with like 4 plates that does the same thing. I did this one when I was talking to CubeSat people, so I was trying to show a CubeSat looking thing, but yeah, same stuff. All right.
Could the antenna work as?
So yeah, I think like, I mean, sort of along the lines of these, there's like a bunch of kind of like systems-y things in here that are like fairly dialed in to like fit everything in a tiny package, right? So I think doing double duties with different things kind of is important here. And yeah, you can imagine doing things with the antenna along those lines. Right now the antenna is already doing double duty as the deployment spring.
Yeah.
So it might be kind of hard.
Triple duty.
Yeah, to make all that work. All right. We're gonna call it right then.
Thanks.
Yeah. Thank you.
Really awesome talk.
Thanks. Yeah, there's like a lot of these meandering.
Yeah, no, it's really cool. It's really interesting. Yeah,
Yeah. I tried to like